Olá, bom dia a todos. Meu nome é Pedro Bertemes Filho, sou professor da Universidade do Estado de Santa Catarina, de Ciências Tecnológicas. Estou aqui para apresentar para vocês esse tutorial que foi apresentado no IEEE SENSORS 2023, chamado de Biospectroscopia baseado em plataformas de biosensoriamento. Foi apresentado na cidade de Viena, na Áustria, em novembro de 2023. A apresentação está em inglês, então I shall speak in English, if you don't mind. So, bioimpedance-based biosensing platform, that's the title of the presentation. The outline will be a bit of introduction theory of electrical impedance spectroscopy, variable sensors for GCM, which is continuous glucose monitoring, wire device for continuous glucose monitoring devices, signal processing and data analysis, clinical application of electrical impedance spectroscopy, and challenges in future directions and conclusion of the tutorial. That's the basic outline of what you are going to see. So, introduction. Biosensing platforms are analytical tools, okay, that detect and quantify biological molecules or processes, all types, all sorts. So, now talking about spectroscopy, what is actually spectroscopy? It's a technique widely used to analyze biological samples, which study the interaction of electromagnetic field in biological samples. So, there's a lot of types of spectroscopy. For example, infrared spectroscopy, Raman spectroscopy, fluorescence spectroscopy, etc., etc. And one of them is impedance spectroscopy. And what we are going to talk about today is about impedance spectroscopy. Not mechanical impedance, vibration impedance, electrical impedance, okay? And what we do usually, we excite the sample with an electrical current and we measure the resultant in terms of voltage, and measuring the voltage divided by the current that we apply to the sample, and we have the impedance. And we do it in a lot of frequency, so that's spectral impedance. And we measure modulus of the impedance and phase of the impedance. Once we have this data, we can apply into an analytical model and extract the parameters of the sample, all sorts of type. And then from the parameters, we can, for example, diagnose a type of cancer, for example. And the application in that case, healthcare, as I said, agriculture, environmental, food safety, drug discovery, forensic science, so all sorts of type, as you can see here. Many applications, not only in biological, but can be in any type of industry. And that's the evolution of biosensors, in a sense. The first one started in 1956. It's oxygen biosensor. Bio because sensor is the element which interact with the physical measure. And bio is only for biological samples. That's one in oxygen biosensors. Glucose biosensor was invented in 1962. Then, as you can see, urea, biosensor, needle, electrode in 1982, and so on. In 200, the new century, they started to introduce nano biosensors, and that's the newest technology. Even now, in 2023, people are using nano sensors, nano robots for detecting macromolecules inside the body or inside in a sample, which can be in vivo or ex vivo. the basic elements for a biosensor is, well, the sample. The sample can be water, air, soil, any type of vegetation, can be any type of food as well. Who will sample? Blood, urine, saliva, what else? Blood, urine, saliva, feces, sperm, for example, as well. Cell culture can be a cell culture for any type. For example, if you want to detect any growing of a cancer cells, you can adapt this cell culture here using a biosensor in order to see if the cell, this cancer cells, is growing or not. But the sample is here. Now we need to use a transducer, and then we have all sorts of type. For example, this is the bioreceptor. The bioreceptor for a biosensor is important. Can be a nucleic acid, cells itself, antibodies, or enzyme, combined with a electrical interface. And that interface can be electrode only, can be nanoparticles, nanowire, or wire itself, or a field effect transistor device. So you need an electrical interface. Combined with the bioreceptor, you have the biosensor. Then, after that, you need to set up an electronic system in order to measure the resultant, the signal after that, and then you need an amplifier or signal processor, or there's all sort of type of embedded system that can be used for measuring the signal from a biosensor. Then some application, as I said, healthcare, diagnosis and monitoring of disease, drug discovery. Drug discovery is being used a lot nowadays. Point of care testing. This is pretty new for rapid and accurate diagnosis of disease at point of care. So you don't need to go to the hospital, you don't need to go to the clinic. You can have your system set up with you, close to you at your home, just taking all the data and sent by, for example, Bluetooth, and your doctor can, medical doctor can see your data, and also your healthcare also can see your data. And environmental monitoring, detection of pollutants, monitoring of water quality, identification of microorganisms is being a lot used using agricultural way. Food safety. Food safety is a promising tool now using biosensor for rapid and sensitive detection of foodborne pathogens and contaminants. For example, milk, one of types, especially in Brazil, that people usually adulterate, and then we can set some biosensors to detect the adulteration. Detection of bacteria, for example, pathogens such as Salmonella, Listerine, E. coli in food sample. And can these bacteria stuff can result in diarrhea? Okay, and diarrhea can leave you into hospital quite quick. Identification of chemical contaminants such as pesticide, microtoxins, heavy metals in food samples, mercury, for example. You cannot eat mercury. Okay, it's not good. No, it's not good. The taste is not good as well. But anyway, it can kill you. Monitoring of food quality parameters such as freshness, spoilage, adulteration, as I said, for the case of the milk. Nanoparticles detection, characterization, and this is also a now now they are calling nanomedicine. And for going to nanomedicine, nanotechnology, nanotoxicology, we need biosensors. There's no way out of it. And the smaller, all the electronic is getting smaller and smaller. Now they are building up transistors as small as 0.09 micrometer. So it is quite small, and going to nano, and then biosensors will be possible because electronic is getting nano as well in terms of transistors. Functional brain imaging, neurodegenerative disease, and neuropharmacology. For example, electroencephalography. It's very hard to detect the signal from the scalp because it contains a lot of hair, and then you have to shrink down the size of the sensor placed at the surface. Then people are using very small electrodes, and also you can insert inside the screw some electronic for detecting, for example, Parkinson's disease, and that contains some biosensor itself reacting with the sample inside the screw. And you need to be biosensor because you need the body not to react against the electronics inside of the body. Well, more applications, immunology, microbiology as well. For example, detection of identification pathogenics, as I said, investigation of bio interactions with other organisms as well. And this is the new technology which is being doing after the COVID-19, for example. People are going down to nanotechnology and then using biosensor in that case. So, big resume of it is that environmental one application, disease detection, water monitoring, toxin, drugs, pathogen, food quality, and soil quality monitoring as well. Now they are talking about agriculture 4.0. Everything is autonomous, everything is automatic, everything is being sensing using a lot of sensors. Even to see if the fruit is ripe or not, they use drones. Go to the plantation and look at the apple and see if the apple is good for harvest, and then the image, see, oh, that's good. So you see another sensor which is putting in the plant as well, in the soil, collecting the air, the humidity, the amount of sun, the UV, etc., etc. Then measuring technique for when you use, well, as I said, the analyte can be antibody, cells, bioreactor, here can be antibody, enzymes, cells, aptamers, and nanoparticles, for example. Can be others as well. The transducer itself, the transducer can be a electrochemical one, optical one, thermal one, electronic, galvanometric, and acoustic, so all sorts. Depend on the application, depend on how much you have in your pocket as well. Depending on the size of your system, you can decide which one you want to go to. And in our case, for impedance, is that it's classified as an electrochemical one. And the electrochemical one, we can measure the current, electrical current amperiometric. We can measure the potentiometric, is the potential that we develop. We can measure the voltage, voltametric. We can measure the conductance, conductometric, but also the impedance, impedometric. So the technology we are proposing in this presentation is an electrochemical biosensor using impedance data. So using biosensing, impedo or potential, it can be one or another. So you have your transducer here. Can be any types, wire, nanopores, can be nanowires, not nano, micro wires, can be a cell like this, can be polymer, can be metal, polymer, conductive polymer, of course. Okay? And then you have your biosensing system, the transducer, that's your potential stat, and this means that there's no wire connection between the signal processing and your device, Bluetooth here. This is the one type of potential stat that people have been using, because using potential stat, that means you can increase or decrease the amount of current that you are exciting the sample. You cannot put a lot of current, otherwise you are going to destroy the sample. So depending on the size of the sample, the type of the sample, then you can choose how many current you want to apply to. The 1 milli, 1 microampere, or 10 micros, this depend on. So potential stat gives you this freedom for choosing the current. Okay? This is the analysis. So the type of the data, output data of these systems is about this. Impedance, real, imaginary part. And then you have a curve. And we say this is a Nyquist plot, okay, in the area. And then once we have the Nyquist plot, we have this, we can model to a equivalent electrical circuit in terms of resistance and capacitance. Perhaps 1 or 2 in series. And then once you have these numbers, we can classify the sample. If it's good, is it good for drinking? Not good for drinking? Is the tissue you're analyzing is normal tissue or cancerous tissue? These numbers will give you the information. Once you have this, fit to this. For getting this, you have to measure using, for example, this. Okay? Well, that's the impedance spectroscopy. As I said, I'm not going to explain here again. I defined it at the beginning of the presentation. People are also saying bioimpedance analysis. It can be the same. Bioimpedance analysis or spectroscopy. Bioimpedance analysis is usually the term that people use for body composition. To analyze the amount of water you have in the body, the amount of feet frame mass you have. Okay? And usually people use low alternating current. Okay? And this is low, probably this is wrong, because half ampere is not small, but when you look to the frequency, 50 kilohertz, and if you look to the standard IEEE 6061-1, that's the standard regulation, the amount of current will depend in the frequency. So probably at 50 kilohertz, it's allowed to use half ampere. Okay, I've never used half ampere. Okay, it's a bit dangerous. But it's fixed frequency, so it's fine. So for example, you have your impedance analyzer, and you can create your sensor here, micro ones, that's the connection. And for example, you put a drop of water, a drop of blood here, and you can extract the data, resistance, reactance, real part, imaginary part. And as you can see, different curves, different radius, 1, 2. So, depending what you have in the sample, is there any virus in the blood? You can see here. If the shape change, let's say, oh, the sample is 100% positive, so you have COVID-19. Sorry. Or you're analyzing a drop of milk, and the milk is horrible, contains a lot of bacteria, and not good for drinking. And you can say straight away. But how can you say, well, you have a good sample of blood and a good sample of milk, and then you can compare. That's a good one, that's not good. Okay? So that's easy, straight away looking to the curve, or you can create a number and you can say, well, that's the radius decrease as the amount of virus of this blood or sample increases. Let's say, just an example. I'm not saying that that's really the case. Okay? So, and that's the way people use for to put electrodes on the body to measure the water content. Okay, for example. But this is bioimpedance, usually known in the medical terms. And the electrical impedance spectroscopy, the advantage is simple, quick, inexpensive, readily used in population study. Non-destructive test like others, spectroscopy, Brahma, destructive. All sorts of type using X-ray, destructive. And free of radiation, radioactive label free as well. You can do in vivo experiment as much as you want. There's no radiation. So it's free of radiation. That's good. The advantage, variability in terms of in the measurement and its dependence on the hydration level of the patient. We are talking about bioimpedance here. So depending how much water you ingest. So there are some people drinking 2 liters of water per day, 3. There are some people drinking more, but there are some people like me drink 1 cup morning and 1 cup afternoon. And this is not good, so you are not taking too much water as you need to. And that amount of water that you take along the day will change your bioimpedance in terms of water content, for example. The water content is not the one you are going to measure because you are being drinking. No, the water content contains in the cells. Okay? 64% of your body is water. 64. So if you don't drink water, you are going to stop one day quick. As the car, you have to put petrol. Otherwise there's no way to run from one point to another. And that's the way people have been doing theory. We apply a current or a voltage. If you apply a voltage, you measure the current. If you apply a current, you measure the voltage. Okay? By the end of the day, you have to have voltage divided by I, which is modulus and the phase of the impedance. And that's the circuit model. And this is contained one element, bizarre, non-uniform element, that we call phase constant element. This is not a capacitor. This is something bizarre. What I'm saying is that our biological sample don't behave uniform as expected using standard elements, circuit element. It's not a capacitor because also as much as we increase the frequency of the field injected in the sample, the amount of charge inside the capacitor will change the size of the capacitor. So this is a bizarre behavior. Depending on the frequency, the amount of storage of charge will also change. So it looks like a capacitor will change the size of it as we increase the frequency. So it is a bizarre behavior. And they model as a phase element constant. So, and we plot imaginary part and the real part, and we have this nice plot, and then we can have a lot of conclusion here. For example, this is slope, this radius here, starting from low, look, right to left, low to high frequency, like this. And this is a constant behavior due to the interface impedance between the electrode, can be a polymer, semiconductor, metal, and the electrolysis and the amount of ions in the sample. Okay? Some people use this very nice for characterizing batteries, for example. This is very important, very low frequency, millihertz. Millihertz. And this is megahertz. Okay? Detection of microorganisms, analysis of human body composition, as I said, quality of food, corrosion, analysis for metal surface, even in cement past. Hardening analysis. Is it the cement nice, hard, nice, or contains some cracks? It's not good. Some pores also can be used. We can use impedance spectroscopy. And then using with biosensor, as I said, this is the impedance-based biosensor. As you can see, we are using two capacitor here. Is a way of represent